Bless your heart. Some kind of way you done found yourself for the online tutoring of Mr. Whittington's. Is it Mr. or Mr.? Mr. Whit? How that man say that? Anyway, today's episode is on factories. Now, I don't know what in the Sam here any of this means, but I hope you enjoy yourself, so get your ink pen and your pencil and get ready to learn about factories.
Hello ladies and gentlemen, this is Mr. Whit with Fort Bend Tutoring, and today's tutorial is going to be about factoring a sum of squares. That's right, a sum of squares. And this topic should be familiar to you if you've been discussing factoring. So that means you've already been introduced to factoring the greatest common factor. You've already tackled factoring trinomials, and now you're about to tackle factoring differences of squares as well as sum of squares. Well, after being introduced to all those different ways to factor, you may have been told that factoring a sum of squares is impossible. That if you have the format of a squared plus b squared in an expression and you're asked to factor it, that the end result of that would be prime. In other words, it cannot be factored. And your teacher and textbook would be correct. It's not factorable. You can't factor this using real numbers. But see, that's the point of this video. The point of this video is to remind you that, yeah, you can't factor this using real numbers. However, you can factor this using imaginary complex numbers. Yeah. See, using complex numbers, those numbers that involve a real number and an imaginary number, you actually can factor a sum of squares. And this is the factoring pattern for that. So if you encounter a problem such as a squared plus b squared and you're asked to factor it, then you can use this factoring pattern, meaning that the square root of the first term plus the square root of the second term times I, then multiplied by that same square root of the first term minus the square root of the second term times I, will give you the result that you're looking for as far as a factoring pattern, as far as answering the question, factor this sum of squares. So let's look at some examples, all right? Here we go. Example number 1. Here it is. Number 1, we have x squared plus 9. If you're in a regular algebra class, the answer to this would be prime. Yeah, it can't be factored. And we can go ahead and put a red box around that. Because that's the answer. The answer is prime. However, if we have this problem, x squared plus 9, and we happen to be in an advanced course, we happen to be in a GT course, we happen to be in a pre-AP course, we happen to be in an AP course. In other words, we're in an algebra class that is accelerated and you've already encountered complex numbers, meaning those numbers that involve real numbers and imaginary numbers, then you actually can open up two sets of parentheses here, and then you'll take the square root of x squared, which is x, that'll be your first term. You'll then take the square root of 9, which is 3. However, you'll need the imaginary number I, since this is a sum of squares, and we'll need to have imaginary numbers in order to make this product work. And just like a difference of squares, you'll need one of your second terms to be a positive and the other to be a negative. And if you haven't been keeping up with me, I prefer to put a positive first because I'm an optimist. Okay? Only negative people, pessimistic people, put the negative sign before the positive sign. I'm just saying. Okay? Brighten up your life. Okay? Be happy. It feels good. All right. So bottom line, this is the answer. This is the answer. And I'm going to put a red box around this because that's the way I roll with my answers. And I'm going to go ahead and verify this result. That's right. I'm going to multiply it out to prove that this is correct. So verifying this, I'm going to go ahead and get my arrows popping, ladies and gentlemen. That's right. I love the distributive property. So multiplying x times x, I get x squared. Multiplying x times negative 3i is negative 3xi. Then multiplying 3x times I get a positive 3xi. Then multiplying 3i times negative 3i, I get negative 9i squared. Notice how our middle terms here will be canceling out. That's right, they're additive inverses, so they'll cancel. Then bringing down my x squared term, like so, I'll also bring down this negative 9, and I squared just happens to be negative 1. So recall that I to the second power, I times I is I squared, and that is equivalent to negative 1. Then multiplying negative 9 times negative 1, that'll give you a result of x squared plus 9, which verifies that this is correct. There you go, ladies and gentlemen. So this is the process for factoring a sum of squares. You got it. All right. So depending on your course, your result for your answer of a sum of squares will be either prime, meaning that it is not factorable using real numbers, or you'll have this answer here, x plus 3i times x minus 3i, using complex numbers. So you'll know if you're able to use these in your class by one, asking your instructor, of course, or you'll already have covered imaginary numbers in your class, and then you're asked to factor this sum of squares. That'll give you an inclination, a clue, that you'll be using this factoring pattern in order to factor a sum of squares. All right, so that's the first example. Let's move on to the next one. In our next example, we have 25m squared plus 16n squared. So I do recognize that the first term is a perfect square. I also recognize that the second term is a perfect square. We got a plus sign in between them. So therefore, this is a sum of squares. So once again, depending on your course, this answer will be prime. Yeah, it'll be prime. You can't factor this using real numbers. Or you can open up two sets of parentheses, like so. And the square root of 25m squared is going to be 5m. All right. Like so. And the square root of 16n squared is 4n, but remember, we're going to be putting 4ni. 4ni, that imaginary number, is going to be included with that second term, and because I'm an optimist, yeah, I'll be putting a plus then a minus sign in here, and this is the answer. That's it. 5m plus 4ni times 5m minus 4ni, and done. That's it. I'm going to put a red box around my answers. All right, let's go ahead and box that up. So this is going to be for your regular algebra class, that it cannot be factored. It is prime. It cannot be factored with real numbers or using imaginary numbers. This is the AP answer. You're going to have this right here. There you go. That's problem number 2. Moving on to problem number 3. All right, with problem number 3, we have 4x squared plus 64. You should already know and be aware of the fact that, yes, this is a sum of squares. That first term is a perfect square. We have a plus sign, so it's a sum. And then the second term is a perfect square. That 64 is a perfect square. It is. And so this is a sum of squares. However, when asked to factor, you should always look for the GCF first, that greatest common factor. And these two terms do have something in common. They have 4 in common. And no matter what class you're in, you're going to be factoring out the GCF of 4 first. That's right. So factor out that 4. That'll leave you a quantity of x squared plus 16 within the parentheses there. And this would be your answer. Just like that. You factored out the GCF of 4, and you end up with 4 times x squared plus 16, knowing that what remains inside the parentheses is a sum of squares that's not factorable. That's if you're using real numbers. So this would be your answer. Let's go ahead and box that up. All right, so this is what you would have if you were in a regular algebra course. There you go. No matter whether it's college algebra or whatever, this would be your answer. You couldn't factor it any further. Or if you're in an accelerated class and you've already been introduced to complex numbers, you can factor this sum of squares using imaginary numbers. So this is what you would do from there. From this point, we would just continue. We would bring down our GCF of 4. We would open up 2 sets of parentheses here, and you would take the square root of x squared, which is x. So that's your first term in your binomials. And the square root of 16 is 4. However, you would use 4i as the second term in each binomial, being as though you'll need imaginary numbers in order to complete the factoring pattern for a sum of squares. So now, what am I going to do next? Exactly. I'm going to put a plus sign in this first binomial and then a negative in the second one. That's what I'm going to do. But you may be a pessimist and you may put a negative sign first, which is fine, because that's how you roll. But I don't roll that way. So there you go. So now I'm going to put a red box around this. That's what I'm going to do. Are you at least with me on the red boxes? Can you at least agree with me there that no matter whether you put a plus or minus sign first when you're factoring your sum of squares, that you can at least agree that it needs a box? It needs a box, okay? We're gift wrapping our answers for the instructor, all right? So it's Christmas every day here. So anyway, so that's it. That's it. These are the 2 results that you would be looking for. One, the first result is for a regular algebra course. All right, you still have to factor out that GCF of 4. But then in your class, you wouldn't be able to factor it any further because you're only restricted to using real numbers. However, in an AP course where you've already been introduced to complex numbers, you're using imaginary numbers, and you've already been shown examples of these type of results in your class, then this is the answer that you're looking for. You would want to factor that sum of squares using imaginary numbers. There you go. That's it. These are the answers for problem number 3. Done and done. Moving on. Problem number 4. This is what we have. We have 8c squared plus 98. So no matter what course you're in, you should recognize that you have a GCF of what? What do these two terms have in common? Do you know? Well, do you? Exactly. You're exactly right. They're both even numbers. They both can be divided by 2 evenly. So therefore the GCF is 2. So let's go ahead and factor that out. You got it. So factoring out 2, you'll be left with 4c squared plus 49. There you go. And in a normal algebra course, this is your answer. You can't factor a sum of squares in that course using real numbers, so therefore this is your answer. But the answer is not prime because you actually factored out the GCF of 2. So you did some factoring. You factored out the 2. So you're good to go. Put a red box around that. There you go. There you go. Here's my red box. Here's my red box. And that's the answer for a normal algebra course. There you go. Now, let's look at an AP course. Let's look at an accelerated course that's just going all out to drive the students crazy. What would you need to do? You would need to continue this process and factor that sum of squares. That's what you would need to do. So let's go ahead and do just that. So now, bringing down that GCF of 2, I'm going to open up 2 sets of parentheses, and then I'll be taking the square root of that first term inside of the parentheses here. The square root of 4c squared is 2c. All right? That's the first term inside of my parentheses here. Then you're going to take the square root of 49, which is 7. However, since this is a sum of squares, remember, using our factoring pattern that I showed you at the beginning, you'll need to write this as 7i. All right, there you go. And because I'm Mr. Wet, I'm going to put a plus sign and then a minus sign. All right, positive before the negative, ladies and gentlemen. That's right. Give me the good stuff first, and we'll deal with the negativity at the end. There you go. I'm going to put a box around this. This is the answer to problem number 4, ladies and gentlemen. That's right. Putting a box around my answer. Are you boxing up your answers? Just go ahead and box them up. Box up your answers for your teacher. God. Now moving along. We're on to problem number 5. That's right. With number 5, we have negative 36y squared minus 121. So what do we need to do first here? You always start every problem that asks you to factor by factoring out the GCF, the greatest common factor. And anytime the first term is negative, you're going to be factoring out a negative something. All right? A negative something is coming out of here. All right? So let's make that happen. So no matter what course you're in, if the first term is negative, factor out a negative something. There you go. So what is this something that I'm referring to? Well, do the terms other than the negative have anything else in common? No, they don't. The 36 has nothing in common with the 121. That y squared is not happening with the second term. There's nothing that these two terms have in common other than the fact that negative 1 can be factored out of both of them. So that's exactly what we'll do. So factoring out a negative, you'll end up with 36y squared plus 121. And in a normal algebra course, all right, you know who you are. You know who you are. This is going to be the answer. Yeah, there's nothing else you can do with that. Okay? And the answer would not be prime because you were able to factor out a negative 1. You see? So this is going to be your result. That's the answer right there. That's what your teacher would be looking for. Let's go ahead and box that up. So this is the result for a normal or regular algebra class. There you go. Whether it's Algebra 1, Algebra 2, Pre-Calculus, or even College Algebra, this is the answer that you're looking for. Now, if you're in an AP course, you're in an honors course, or you're just nuts for mathematics, like I am, then you're going to go ahead and continue factoring this using imaginary numbers, complex numbers. So here we go. We'll bring down that negative. We'll open up 2 sets of parentheses here, and the square root of 36y squared is going to be 6y. There you go. That's what's up right there. Then I'll be taking the square root of 121, which is 11. I. That's right. Don't forget the I. Okay, and that's 11i over there. Okay, it's supposed to be 11i. It's not going to fly, is it? No, it's not going to fly. There you go. That's a better 11, is it not? Okay, will you forgive me? Oh, now you're complaining about that one right there? Okay. You guys are being real picky today. Real picky. Is that a better 11 for you now? Okay, that's the best it's going to get. And then what would I do next? I have my GCF. That's a -1 right there. That negative sign, all right, is the GCF. And I have the square root of 36y squared, which is 6y. I have my 11i, and I'm going to lead with a positive. Thank you. Then a negative. There you go. That's the answer. That's it. That is our factorization for this problem. Number 5, -36y squared minus 121. Using complex numbers, your answer is going to be the opposite of the quantity 6y plus 11i times 6y minus 11i, and done. Yeah, it's done now. I'm moving on to the next problem. All right, so there you go. Next, we have this. We have problem number 6. We have 16x to the 4th power minus 81. So let's go ahead and factor that out. And you're not crazy. This is actually a difference of squares. It is. Yeah. So why am I doing a difference of squares problem in the middle of my factoring a sum of squares video? Let's find out. Let's see. All right. So first things first, no matter what course you're in, you should recognize that the first term is a perfect square. You have a minus sign. And the last term is a perfect square. You should notice that. Okay. Just saying. So going forward, we're going to factor that. Okay, all right, let's factor that out. The square root of 16x to the 4th power is 4x squared. All right, there you go. That's for you. And then the square root of 81 is 9. There you go. I'm going to have a plus and then a minus, like so. All right, great. Then I'm going to continue to factor this. That's right, because the second binomial is a difference of squares, which is factorable, all right, using real numbers. So I'll bring down that sum of squares, yeah, I sure will, that 4x squared plus 9, and I'll open up 2 sets of parentheses for this difference of squares here. That second binomial, that 4x squared minus 9 is a difference of squares. So you need to factor that. The square root of 4x squared is 2x. Yeah, it is. Okay, and then the square root of 9 is 3. Thank you. I'm going to put a plus and a minus. And this would be your answer in a normal, regular algebra course. That's right. I'm going to box it up. Going to box it up. Hopefully you've been convinced by now that you need to box up your results. Just saying. Put a box around that thing. Okay? Thank you. Now, that's the answer. However, if you're in an AP course, you need to factor the sum of squares as well. So let's do just that. Okay, so we're going to go ahead and factor this, making sure that we factor that sum of squares now. I'm going to open up 2 sets of parentheses just for that and bring down the rest. Bringing down the rest. So here we have it. The square root of 4x squared is 2x. So I have that there. I have that there. The square root of 9 is 3. However, since this is part of a sum of squares, I'll need a plus 3i and a negative 3i, all right, for my second terms there in those first 2 binomials. Then I'll be bringing down these last 2 binomials as is. So this is going to be the 2x plus 3. This is going to be 2x minus 3, and done. And done. That's it. This is going to be my final result if I am using complex numbers in my course when factoring, ladies and gentlemen. This is the answer. There you have it. Nice box just for you. And those are the 2 results that you can submit, ladies and gentlemen, depending on your algebra class and teacher for that matter. All right, so there you go. That's problem number 6. Let's continue. And in problem 7, we have the following. We have 256c to the 4th power plus 81. This is a sum of squares. Recall that anytime you have an even exponent, that automatically makes that term a perfect square. All right, so if that had been c to the 8th power, c to the 24th power, it's automatically a perfect square because the exponent is an even number. Okay, all right, so if you're in a regular algebra class, the answer to this is prime. There you go. It's not factorable. You can't factor this using real numbers. It's a sum of squares. You can't factor that. Boxing it. Red boxing it. Just like that. There you go. However, if you're in an AP course and you're given 256c to the 4th power plus 81, and you're asked to factor it, then you can factor this like so. Let's open up 2 sets of parentheses here. And the square root of 256c to the 4th power is going to be 16c squared. All right. And then the square root of 81 is 9, but we'll need a 9i, won't we? There you go. And so I'll lead with a positive, then a negative, and this is the answer. That's right. You can't go any further. So even though this appears to be a difference of squares and this appears to be a sum of squares, it's not, because your I is to the first power. Okay? So it stops right here. That's the answer. Let's red box it. Red boxing it, ladies and gentlemen. There you go. So these are the answers for problem number 7. If you have this problem in a regular algebra class, the answer is prime. It cannot be factored. It cannot be factored. It cannot be factored. Just saying. Just saying it can't be factored. However, if you're in an AP course, you guys have already covered complex numbers, and you're asked to factor this problem in that course, then yeah, you can end up with this result right here. Yeah, that was problem number 7. And I have one more problem for you. Are you ready? Because here it comes. There you go, ladies and gentlemen. This is problem number 8. This is our final problem for this video, and I hope you're ready. This is 6x squared plus 5. That's exactly what it is. Notice how 6 is not a perfect square, 5 is not a perfect square. However, we will be utilizing the positive square root of each of these in order to factor it. So let's look at that. All right, so let's go ahead and open up 2 sets of parentheses here. All right, so there we go with that, there we go with that. Just like this. And so the square root of that first term, that's 6x squared, we're gonna write that as x times the square root of 6. Just like that. And the reason why I'm putting x in front of the radical is because I don't want you to make the mistake that my x is underneath the radical symbol, because it is not. All right, so I'm going to put it in front of the radical sign. And I'm going to do that for the second binomial as well. So there you go. All right, so the square root of 6x squared, I'm writing that as x times the square root of 6. Then the square root of 5 is going to have the following result using our imaginary number I. I'll have I times the square root of 5. All right, just like that. Once again, I'm putting the I in front of my radical so that you don't mistakenly believe that the I is underneath the radical sign. All right, and then, as always, I'll lead with a positive and then a negative, and this is my answer. All right, and let me go ahead and show you a version of this where I actually place the radicals in front of the x and the imaginary number. All right, so depending on your instructor, they may not even care about the aesthetics of things. They may want the radicals to be in front of the variables and definitely in front of the imaginary numbers to keep your result in A plus BI format. All right, so that being the case, I'll have the square root of 6 and then put a little space there and put your variable x, and then it's going to be plus the square root of 5 and then put a little space there and put your imaginary number I there. All right, and then you can do the same thing in the second set of parentheses. You can have the square root of 6 and then a little space here and then your variable x, and then you'll have your minus sign, and then you'll have the square root of 5, a little space, and then the imaginary number I. All right. You could write it that way as well, but once again, you'll have the drama of making sure that this x doesn't look like it's underneath the radical and that this I is not underneath the radical. All right, just saying. So that's why I prefer this version of the result, because clearly x is not underneath the radical sign, and clearly my I is not underneath the radical sign. All right, because that would be a totally different answer and it would be wrong. It would not get you back to your original result of 6x squared plus 5. All right, so there you go, ladies and gentlemen. This is the answers for problem number 8. All right, and once again, if this was just a regular class, just saying, the answer would just be prime, not factorable. You would just go just like that and be done with it. So let's go ahead and put a box around these versions of our answer for problem number 8. All right, so in a regular algebra course, prime, not factorable. Not factorable. And then if you're in an AP course and you guys are using complex numbers and you guys are using the positive square roots of numbers, all right, for factoring, then you'll have either of these versions here. So I'm going to box both of them up, and you can go ahead and run these by your teacher to make sure which version they prefer. This, ladies and gentlemen, has been Factoring a Sum of Squares with Mr. Witt and Fort Bend Tutoring. And as always, please rate, comment, and subscribe. Those are important to us. Thank you very much. And if you're able, please donate, as that helps us bring you more free math tutorials from me, Mr. Witt, and Fort Bend Tutoring. Peace.
FACTORING. This includes topics such as GCF, that's the greatest common factor, like Obama, the difference of squares, quadratic trigonometry, oh Lord, that's when the pig is sick on all 4 sides, the sum of cubes, that sounds like one of them games they play, difference of cubes, oh that's just ignorant. AC method, yes honey, because you got to have your air conditioning in Texas. And factoring by grouping.